Hi, today's video is going to be a little different in that I'm going to be answering your physics-related questions. They've been posed to me at various times since I started this channel. I got the idea from Steve Shives' channel, where he regularly answers his viewers' question. I think it's a great way of interacting with my audience. On your part, you get to actually have questions about physics that you want answered, and on my part, I get to see what physics interests the people who watch this channel. So if you have a question for a future video, be sure to mention it in the comments. Also, stay tuned for a weekly channel recommendation after the science. Does the sun produce antiprotons? This question was sent in a while ago, and I haven't actually managed to track down the person who sent it in. The answer to this one is no. While the sun can produce anti-electrons, or positrons, it cannot create antiprotons. Even though the sun is incredibly hot, it's nowhere near hot enough to actually create antiprotons or antineutrons. From Einstein's formula E equals mc squared, the amount of energy needed to create something from nothing is proportional to its mass. Let's represent the energy needed to create a proton using money. Say the amount of energy in a proton is worth $10. For reference, that means the amount of energy in an electron is worth about half a cent. That means that in order to produce an antiproton, you need to supply $20. The reason for this is because in order to create an antiparticle, you have to also create a standard particle. So $20. Now, how much energy do you think a typical fusion reaction in the sun has? Well, if you look at two deuterons fusing together to create one helium-4 nucleus, this would produce about a quarter. Not a quarter of the energy needed to make an antiproton-proton pair, but a quarter as in 25 cents. And that's actually one of the more energetic reactions going on in the sun. You might be tempted to think that it's possible for the sun to save up its quarters, sort of like you did your allowance when you were a kid, and eventually store up enough energy to be able to produce a proton-antiproton pair. Sadly, that's not how things work in the sun. Almost as soon as the energy of a fusion reaction is created, it gets dispersed into the plasma of the sun, heating up a little bit. So no antiprotons for you. The next question is, what's my position on string theory? Well, first, disclaimer. I am not a string theorist. I've never been a string theorist. I mean, I don't have any problem with them. Some of my best friends practice string theory. It's just, not my choice of lifestyle. Well, there was one semester back when I was in undergrad, but we all experiment a little in college. A bit more seriously though, my position on string theory is a little mixed. I mean, on the one hand, it really is, so far, our best attempt at unifying the quantum with gravity. And that's a really tricky thing to do. Not many other theories even come close. On the downside, none of its predictions for how the universe works have been able to have been tested yet. And that's a big red flag for a theory. Now, it could be that this theory is just before its time, sort of like Da Vinci's drawings of helicopters. I mean, even if he'd been given a lab to work with, he wouldn't have been able to build a working one just because materials weren't there yet. So that might be the case with string theory. Somewhere off in the future it will be the theory of everything, but at the moment it's not. I still fully support funding it though, because the potential reward is so big, real fundamental understanding of the universe, and the cost is relatively low. I mean, you don't have to have a big lab to do string theory. You can just do it on your computer or with a pad and paper. So, thumbs up to string theory research. For those of you who don't remember, about a year back, the news exploded about how physicists had discovered a neutrino that traveled faster than light. And I think I can sum up the stance that almost every physicist in the world had at that point, which was, this is almost definitely some kind of experimental error, but wouldn't it be awesome if it weren't? And unfortunately, it turned out that it was a poorly calibrated machine. See, there was a loose cable connecting a GPS device to the rest of the experiment. This caused a small delay in the signal, which made it look like the neutrinos were traveling faster than light. So, disappointing end to an interesting story. So that ends the question portion of this video. As I said before, if you have a physics-related question, please post it in the bottom bar, and I'll see if I can get to it in a future video. If you want to recommend a channel for a shoutout, please do the same. I'm always glad to hear about new and exciting channels. They don't have to be about physics. I mean, I like science channels in particular, so anything science-related would be great, but it doesn't have to be that. This week's shoutout is for the Cosmic Web. It's a channel run by a professional cosmologist and their student. They do these awesome videos on subjects like dark matter and dark energy, and they have quite a clever approach of running their videos by high school students before posting the content. It makes sure that the videos are clear and easy to understand. I've considered doing the same, but it seems like hanging out outside of high school and giving kids videos from the internet is probably a really good way to get me into a lot of trouble. So, without further ado, the Cosmic Web.
Hello everyone, this is the Cosmic Web, and we are part of the Glimpse Science Network. At the dawn of time, in an extremely uniform universe, small perturbations allowed gravity to clump matter in denser and denser regions, and voids to grow ever larger. Galaxies formed, and some were trapped in clusters. These clusters are still interconnected by filaments of mainly dark matter and some galaxies. They constitute the Cosmic Web,